So the first thing is the time for midterm. So if everything goes smoothly, we should be able to finish all the materials in 5 lectures. And that will be leave us to October the 8th. That's the final lecture before midterm. And then I will send out the midterm on October 9th. That's Friday. And then you will have 2 weekends to finish the midterm. And I think I've said it before, but then just to make it clear again, well, technically every class is take home now. Every exam is take home now. Take home exam, and then the time limit is 8 hours. Okay, 8 hours, and you can take 5 arbitrarily long break. For example, you can open it and then read it and then live there for a week and then come back and do it. That's perfectly fine. And I actually encourage you guys to take a quick look at the exam, like when it's released, because you can kind of plan, okay, how long it would take me, and then what are the materials I need to study before I actually work on it. And then the 8 hours doesn't mean that it takes that long. Okay, the 8 hours is that I found in the past is that some students are very hardworking, and then they won't give up until they solve the problem, and they end up losing GPAs or losing scores on other classes, right? Because what I found in quantum mechanics is that if you don't know, you don't know. 8 hours and 18 hours has no difference. So 8 hours is just to prevent you working too hard on it. Okay, and in the past I actually gave 6 hours, and then one student said that she actually has to spend 6.5 hours, so I actually extend to 8 hours. Personally, for me, it took me roughly 40 minutes. So like if you know what you're doing, then it's perfectly fine. And then the exam will be open book. You will have internet access. You can look online, all the textbooks, lecture notes, homework solutions, lecture videos, and Wikipedia. And you're not encouraged to search for the exact problems, because that defeats the purpose of the exam. But you can try, because those problems are homemade. You can't find it on the internet. Yeah, if you can find it, that means you're really good. You're really good at Google, so that you can get some credit as well. And then the other thing is that when you look at the exam, okay, what to expect, and this is something I actually learned while I get to UVA, is that a lot of professors try to babysit you guys, okay, and you all get a nice looking score. That's not the education I received. Like I remember the first college midterm I took, the average score was 40 points out of 100 for the entire class. So and that's the way it is for the next like 5 or 6 years for me. Yeah, and then I think it actually makes sense, because if you're 90 and then your friends is 92, and then I say one is A plus one is A, it's not convincing, right? Because it can be a small mistake. It doesn't really mean anything. But if you're 60 and then your friend is 40, then you can be A, your friend is A minus. That makes a lot of sense. There's 20 points difference. So so the reason that the exam is probably a little bit more difficult than the one you usually see in UVA is because the differential will be a little bit larger, and then it's very easy to give you a grade, right? So the final grade, the letter grade, A, B, C, D, will be curved. Okay, will be curved. And from what I've seen, you guys will be clustered into different groups. Okay, a few of you would be plus 90. Majority of you would be around 70 to 80 somewhere, and then a few of you might be below that. And so we're A plus, A minus is very clear. Okay, so nobody get complaint. And then for the raw score, the median will be somewhere around 75 plus minus 5 points. And for this year, even if it's a little lower, that's fine because we're doing online, right? So so it's not the lecture is not as good as previous years, but this is what I expect for you guys. And then so if you somehow take an exam and say, okay, there are 20 points, I don't know what it is, that's fine. You're still above average, right? So yeah, that's about the exam. Any questions? Okay, good. And then during the week of the exam, you won't have homework. Okay. And I think the minimum points ever in my exam was like 30, and then the students still pass. Okay. Yeah, I don't see any point of failing a student, especially in online format. But then if you turn in a blank exam sheet, then I have a good case to fail you in that situation. Okay, now let's get back to the class content. So previous class we mentioned that we talk about the operator, and then this is the equation for eigenvalue or eigenfunction equations. Operator act on a function, wave function, give you a number times the function itself. Okay, the way to think about it is that this wave function is invariant under this operation. So there's a symmetry between these two. And then we show that because in the measurement, all the values you can measure physically is the eigenvalues. And then because in a physical measurement, you can only measure a real value. You can't get imaginary numbers. So that means an has to be a real number. And we show that for that to happen, then your operator, is a Hermitian operator, which can be defined as the complex conjugate transpose of your operator is itself, or you can kind of define it in this way. This is a self-adjoint definition, okay, mathematical definition. And then in this class, the two most common operator you will see is x, okay. X operator is just x. What it means is that x act on the wave function is x plus ix. Okay, and then the momentum operator is also very commonly used in quantum mechanics. And then if you have momentum operator act on your wave function, equals doing a differential on your wave function, or taking the slope of your wave function. Okay. Now let's move on to the next very commonly used statement in quantum mechanics. Is actually here we can derive from Hermitian, but actually you don't need that. Is that for these eigenstates, they're actually orthogonal to each other. Okay, they're orthogonal to each other. And you can turn to lecture notes, page 31. It's actually said there, for eigenstate without degeneracy, meaning that all eigenvalues are different. Degenerate means, two eigenstates correspond to the same eigenvalue. That's degenerate. For the case without any degeneracy, then the eigenstates are naturally orthogonal to each other. It means that when you solve it, the eigenstate, they're just orthogonal. You don't even need to do anything. Okay, and then we've seen that the orthogonal definition is just to do a inner product between two functions. That's the orthogonal. So let's prove this. Prove the orthogonal of the eigenstates. Okay. Now let's assume that there are two eigenstates that belong to different eigenvalues. So the first one is psi n, and the eigenvalue is an. And the second eigenstate is psi m, and then the eigenvalue is am. Okay. So this is very general. We are not saying what is A and what is psi. Just in general, if you have two eigenvalue, have two eigenstate, and then they belong to two different eigenvalue. Right. Then how can we show they're orthogonal? Right? Orthogonal means that if you do inner product between them, you show that it goes to 0. That's the definition of orthogonal. So the way that we can actually prove this is by calculating this in the Hermitian equation. So let's say you act A on psi n, and then take conjugate psi m dx. Right? What it does is that this Hermitian condition is true for any wave function psi 1 and psi 2. Right? So what I do now is, okay, now let me let psi 1 equals psi n, and psi 2 equals psi m. Okay, very simple. And if you do this calculation, then what you will get is that A acts on psi n because it's an eigenfunction. So it will give me an psi n psi m. Right? It will give me this. This is by definition of the eigenfunction. And then an is just a value, and it's a real value, so we can take it out of the integral. So it becomes this. Okay, so if you look at this, this is very similar to what we're trying to solve here, right? We're trying to solve, we're trying to show this integration is 0, and now we get this integration multiplied by a real number. Okay. Now the second part that we can do is that the other way that we can calculate this integration is by using the fact that A is Hermitian. Right? A not only equal to this part also equal to this. So because A is Hermitian, okay, this is also equal to just let 1 equal to n, m, 2 equal to m. Right? Use a Hermitian condition. And then arriving here, okay, just learn from previous calculation, the simplest thing we can do is to use the fact that psi m is the eigenstate again. Right? So A act on psi m equal to a number times psi m. So this is psi n am psi m dx. Right? So this is a number, so you get it out. Okay? And these two equal to each other, right? Because we're just using two different ways to calculate this, the starting point here, right? So if you say this equal to that, then what you get is an integration psi n psi m dx equal to am psi. Right? And we already know that an and am, they don't equal to each other. Right? That's our assumption. There's no degeneracy in the eigenstate or eigenfunction. So this doesn't equal to that. Okay? But this equal to that, right? These are the same thing. So the only way that you can have a number multiply a number equals to that number multiply a different number is that this number is 0. Right? Or the other way is that you can move this to this side, and then you can, the formal way to do it is this equivalent to am minus am okay, move it to this side, you can do it this way. And we know this is not 0, so this has to be 0. Okay, so this is the orthogonal condition of the eigenstates. So the way to think about this, so how you understand eigenstate? The way to think about this is that you can imagine them almost the same as your Fourier basis, Fourier series. Okay, when you do Fourier transform, okay, when you do Fourier transform, this is a basis. Okay, this is basis, and then they are orthogonal to each other. Think about it. If you do this integration, it's actually go to 0 or ill-defined if omega 1 is not equal to omega 2. Okay, so another way to kind of imagine this is that if you want to express a space, for example, 3-dimensional space with a coordinate with 3 axes, right? And these 3 axes better to be orthogonal to each other, right? So the eigenstate actually provide you this very handy way to construct your axes, and they're naturally orthogonal to each other, right? Okay. And one more thing is that you can say, okay, you derive this based on an not equal to am. What if there's what if there is degeneracy? What if some eigenstates have the same eigenvalue? So in that case, the eigenstate you solved, they are not naturally orthogonal to each other. But then you can always construct a group of eigenstates that are orthogonal to each other. So the way that you can picture this is that, let's say you have 2 vectors, alpha 1, alpha 2. Okay, say they are this eigenstates, right? Because states and vectors are just vectors are 3-dimensional, states are infinite dimension. And you see they're not orthogonal to each other, but then you can always say, I can pick the eigenstate, one is alpha, the other is alpha 1, okay, minus alpha 1, okay, let's see. Alpha 1 minus k alpha 2. Right? You can do a linear combination of these two to create a vector that's orthogonal to alpha 1. Right? By doing this, for example, you can do this. It's actually alpha 2 minus k alpha 1. Okay, this is k alpha 1. Okay, then you get a vector pointing upwards. So when you have eigenstates, they belong to the same eigenvalue, and then they are not orthogonal to each other, then what you can always do is say you can do a recombination of a linear, you can do a linear recombination, and you can always find a group that they're orthogonal to each other. And then the choice of the group are not unique. Okay, you can do infinite amount of different groups. Okay. Any questions here? Okay, if no, then we can talk about one more thing before going into quantum well.
How do you know that you're not moving the problem?
Sorry? Go
like
on.
When you change your basis and you go over to like a new eigenvector, how do you know that new eigenvector isn't going to be not orthogonal with all the other ones?
Yeah, so the way that you, so this one, in linear algebra, there's actually a way to construct orthogonal basis. So the way is that, for example, if you have let's say vector 1, 2, 3, and then the procedure to do that is, okay, you first select vector 1, okay, and then if vector 2 is not perpendicular to vector 1, then it means vector 2 has the components of vector 1, right? So then what you do is you have the second is vector 2 minus the components minus to subtract the components it has in vector 1, right? And if you subtract that, then you can guarantee this one is perpendicular to that one. And then you have to keep going. The vector 3 is you now subtract the components in basis 2 and then basis 1. So you just keep going, and then this is kind of a mathematical procedure to construct an orthogonal basis. And then I think to answer your question is that, so if you start with a different alpha 1, you will get different bases, right? Let's say I don't start with V1, I start with V2. Then this thing would be completely different. So that when you construct a basis, you have to do it like all at once, okay? And then you choose one basis, and that's it. You can't say, okay, I select this, and then in the middle I switch. Then those two would not be orthogonal to each other. Does that answer your question?
Yeah, because then, okay.
Yeah, and remember this, you only have to do this if there's degeneracy in your eigenstates. Okay.
Does that mean you have to change all the eigenstates?
No. Just change the one that are degenerate. Because you can see here, okay, if there are several states, let's say psi n1, psi n2, psi n3, let's say there are 3 states that they all have eigenvalue of an, okay? And then from here you can see that no matter if it's n1, n2, or n3, as long as your eigenvalue is different from am, then this am is orthogonal to this eigenstate.
Okay.
Yeah. So that, yeah, you only have to do this for the states that are degenerate. Okay, you don't have to do it for other states. A very good question. Yeah. And you would not need to do this in any homework or exams in this class, because degeneracy is not, or in general we don't, well, degeneracy is very interesting in the physics sense, but normally we don't use them. Well, we don't need to understand them to understand quantum mechanics and quantum technology, so we kind of skip this. So eventually, well, one more thing that we need to talk about before we move on to the actual quantum system is, previously we say that AN, the eigenvalue, is the measurement result you can get. And then if you have a state, and if you expand it into linear superposition of the eigenstate of A, then the probability of measuring eigenvalue AN equals to the coefficient amplitude square, right? But then there's a problem here is that you have to solve this eigenstate every time, right? If you want to measure something, right? If you want to measure position, you have to solve one. Momentum, solve another one. Angular momentum, again, you have to solve another one. Of course, physicists figure out some ways to solve to do this, like using the operators that commute. But we're not going to talk about that in this class. But here is what I want to say is that there's actually a way to bypass this if all you want to know is the expected value or average value of the measurement, right? Let's say, for example, like in your measurement, you don't have the ability to count individual electrons or individual photons. So when 100 photons come in, what you can only measure is the average value, right? Then there's no reason to go in there and calculate individual probability. The only thing you need to do is to calculate this average value. Right? A lot of quantum measurement is actually done in this way, including the quantum measurement done in my lab. Okay, it's also measuring the average value. And in general, counting individual electrons, photons, atoms are extremely expensive. Okay, for example, in our case, if you want to count single photon, okay, I do. My lab is an optical lab. There's actually a photon number resolving detector in physics department which worth $400,000, and then it's in a huge fridge. Okay, so normally we avoid doing that because, we're not, well, yeah, I don't have to explain further. So how to do this, okay? I can write down the conclusion here first and then show you guys the math a little bit later. So if you just want to calculate the expected, then you can apply your state. Your state doesn't have to expand it in the eigenstate per psi, as long as you know the function. Okay, as long as you know the function of the state, okay, and then your operator act on per psi x, and then dx. You do this integration. So this simplifies the process by skipping the eigenstate equation. Okay, you only need to know your wave function, and this you will solve it by using Schrodinger equation. Right. So after Schrodinger equation, in principle, you know all the expected value that you can measure in your experiment. You only need to do this simple integration. Okay, and let's prove it very quickly. By definition, what is expected value? Right, expected value is that if you do this measurement many times under the same condition, then what is the mean value or average value, right? So then what we can say is that, okay, if my measurement result is AN, and what is its probability? The probability is alpha n squared, right? And if I sum all of this probability times the value, it will actually give me the average value. Okay, it will actually give me the average value. So now what you can do is that to do this calculation, what you can do is that you first write down per psi n. If you look at this calculation, the structure, right, there are two things you notice. First is there's a sum here. And if you need to construct something with the sum, you kind of have to use this one, right? Because this equation has a sum here. And the second thing is that this is not just alpha, but alpha amplitude square. Right? So in some places, you might have to multiply the complex conjugate of this one, because that will give you alpha n conjugate, and multiply with this will give you the amplitude square. So let's first look at this one here. And now, of course, you need to apply A. That's the way you get an. Right? So let's say if I calculate A per psi x, right? And then I expand x in terms of this. Then what I get is A integration, oh, not integration, sum alpha n per psi n, right? And then A can come in here. Alpha is just a number, okay? A come in here, act on each an. And when you act on each an, you use this eigenfunction equation. Then you get alpha n an and per psi n. Right? So you already have an, you already have alpha n. You just need to make it, and you also have the sum, right? So the only thing you need to do is that you need to get the alpha n complex conjugate here, right? So it becomes the amplitude square. And then also you need to get rid of per psi n, right? And then these two are, this might be the first time you see this, but then this is a very common trick. You can do it again and again. So the first is that to get alpha m complex conjugate here, the easiest way to do is multiply this equation with the complex conjugate of the wave function itself, right? And then what you can see is that this will give you m alpha m, okay, per psi m times what you have here. Okay, and it looks like a mess, but then look what you have. You have alpha m complex conjugate times alpha n. And then whenever you see this, the instinct you should have is that I should do an integration because these two are orthogonal to each other. If you do integration, then you can get it to 0 and then it will disappear. Right? So the natural thing to do here is do an integration. And again, notice that the integration and sum, they're just all sum, and then you can actually exchange their order. So what you get here is you have sum m, alpha m, and then sum, do it this way, and alpha m, alpha n, integration per psi m, per psi n dx, right? And now we can use the orthonormal condition. This integration equal to 0 if m doesn't equal to n, right? They're orthogonal to each other. And this integration equal to 1 if m equals to n, right? You're just integrating. You're just doing an inner product of yourself, and then your wave function is normalized. So this is 1. And then what you're left with is that, what they give you is that if you're doing a sum of n, right, then you only need to keep the term when n equals to m. Okay, so the result becomes m equals to 1 infinity, n equal to m, so it's no longer a sum, and then alpha m, alpha n. Right? And then you have n equals to m, right? So now you can kind of, well, the index really doesn't matter. You can use n or you can use m, right? Just the letter, it really doesn't matter that much. So let's say if we keep m here, then this is a sum m equal to 1 infinity, n equal to m, okay, become this. I think I left out an here, yes, an. Okay, so if you look at this integration, the result of this integration is the same as your definition of expected value of a. Okay, and so therefore, in the future, if in any homework, in any quantum mechanical problem, you're interested in average value, and this is the way you calculate it. You don't need to do do the expansion in terms of eigenstate of A. Okay, any questions? Okay, if there's no question, then we will go into a quantum well. Okay. Now, so in the next 5 lectures, what we're going to do is that we're going to use one quantum system as an example, and then solve it thoroughly, right? And then to show you like what you can do with quantum mechanics for a real system. And if you open the note, I think it's called Note 5 Quantum Well. Okay, on the top it says that you can find corresponding materials in the textbook in certain sections. And we actually will go a little bit more detailed than the textbooks. So what is a quantum well? By definition, okay, by definition, what it is that if you write down the Schrodinger equation, like in one-dimensional space, a quantum well means that your potential well, your potential Vx, has the shape of a well. It's just that straightforward. Like in the middle, you can say that the V here is 0. Here you can say V1. Here is V2. Right? And then because the energy, only the relative energy matters. Right? Like if I'm right now in the ground floor, but then if I go to the first floor, the physics doesn't change. So that you have the flexibility to choose your zero potential well place, zero potential energy place. And usually we choose it to be 0. Okay. And the potential well left side and right side, they don't have to be the same. Okay, they can have different potential energy. And then usually when we say a quantum well, then you'll have an electron inside. It doesn't have to be electron. It could be any carrier, for example, in semiconductor, any carrier that have charge and that have mass. Okay, and it can be positive or negative. So by definition, this is quantum well. And then there are two reasons there are two reasons why we started this. First is that unfortunately it's the only one that, well, it's the one of the two samples that you guys will be capable to solve analytically, okay, without using advanced mathematics. The other one is a delta function, which is in the textbook. We will not talk about that in this class. And the second reason is that a quantum well is actually a very popular device in modern technology. And then if you have an iPhone, for example, the iPhone, if you have iPhone later than iPhone 10, then you have the Face ID there. Okay, the Face ID actually have quantum well in it. And the Face ID, what it is that it's a vertical emitting laser called VESEL. Okay, V is for VESEL, V is for vertical. And then the vertical emitting laser actually have a quantum well structure inside. And then the electron can go from ground state to excited state, excited to ground state, to emit light. Okay, and that's the principle of the quantum well laser, and then that's actually used in iPhone. And probably because iPhone and Face ID, quantum well laser might be the most popular laser, okay, in the entire industry. And then nowadays it's extremely cheap. You can buy like one package less than $10. Okay, and then there are other type of lasers, but quantum well laser is quite popular nowadays. It evolved into quantum dot. Okay, if you think about quantum well, is that you confine it in one-dimensional space. It's a well. But if you have three-dimensional confinement, like in all three-dimensional space, there's a well, then you're kind of sealing the carrier into a small dot, and that becomes the quantum dot. And nowadays, the high-performance semiconductor lasers are usually made of quantum dot. And then if you go to Best Buy, you can actually see TV that says quantum dot TV. Okay, and they actually use the same principle. And I gave it a try 2 years ago when I moved to Charlottesville, and I need a TV, right? And I honestly couldn't see the difference between quantum dot TV and LED TV. Well, the only thing that caught my attention is that the quantum well TV at that time was, the size I want was like $4,000, and then the LED was like $800. So you know, as a normal person who is not super rich, you know, I go with the LED. And I'm not sure about the price right now, but I kind of get what Samsung and LG, they're the primary manufacturers of quantum dot. The quantum dot is a little bit brighter, and then the color is more pure. I get that. You know, but I'm actually saving money for a new technology that would be a laser projector, because for your TV, if you go extra large, for example, 100-inch, or even larger, the one I want is 150-inch. The price actually become ridiculous, because you have to do a layer of emitting light, and then scaling that up is actually quite expensive. And then also the TV become heavy and fragile. So an alternative way to do that, I think, would take over in the future. Not long later, it's probably in 5 years, would be a laser projector. If you guys know the projectors used in the classroom, they actually can go very large, but then the problem is that they are not bright enough, right? So that if you don't turn off the light, the projector kind of look pale. So the laser projector is that you can use laser, and then it become really, really bright. And then the second thing is that the laser is well polarized, so that you can use a polarized sensitive curtain, okay, that block the light from the ambient. But fortunately, that's also very expensive nowadays. It's also in $4,000 range. Anyway, just very into tech, very interested in tech in general. So let me tell you guys how you can actually make a quantum well in a semiconductor, okay, before we go into mathematics. So the simplest way to do it is to grow a semiconductor structure called ABA structure. Okay, you grow the structure. A is a material, B is a different material, A is a repeating material. Okay, and then they're all semiconductor. And let's say this is X direction. And the electron or the carrier will be confined in the B structure. Okay, and then the reason it would do that is because if B is a semiconductor, then you can actually look at its band gap. Are you guys familiar with the band gap concept? Okay, so band gap is that electron can have K is the momentum, E is the energy, and then because semiconductor, it has periodic crystal structure, and then when the electron interact with the crystal, it kind of have, when it scatter, it will have interference effect. Then the net result would be, okay, you will have a conduction band and valence band, and then in the middle, there will be no electron state, right? So electron cannot go there. There's no energy or momentum that satisfy the Schrodinger equation when you solve it. Okay, so let's say if this is the conduction band we use, right? Okay, electron in B stay in this conduction band. Now to make a quantum well structure, something very simple is that you can engineer the band gap of A so that the conduction in material B falls into the band gap, falls into the stop band in material A. Okay, for example, a material can have this and this. Okay, so what it means is that electron cannot just go from B to A because the energy doesn't match. If you go there and then your energy doesn't change, then you're going into the stop band of material A. It wouldn't actually, the electron wouldn't be able to exist there. So the only way that you can go from B to A is that you have to, for example, from conduction band to conduction band, is that you have to acquire additional energy, right? If your electron is here and then you want to go to here, then you have to gain this extra energy. You have to gain this extra energy to go from B to A. And this extra energy is represented by this potential well, right? It's actually the V1 and V2 here, set by the band gap difference between A and B and B and A. Okay, and then the quantum well is actually very useful, relatively easy to fabricate. Is that you can, for example, you can do aluminum, gallium, arsenide. You can do different material systems, and then in the different material systems, you can change the you can first grow a material A, okay, it's a certain proportion of aluminum and arsenide, and then when you start to grow B, you just change the composition a little bit, and then that will shift your band gap. Okay, so the technology that used to create quantum well is called thin film deposition. Right, you grow a layer, and then you grow a next layer, and then you grow a next layer, and then keep going, and then you will get a quantum well. And you can kind of sense now why the laser you use in phase ID is vertical, Okay, because if you keep growing this layer, if this is simple, then eventually the laser will go in this direction. Okay, and then it would be vertically emitting compared with the plane your laser is grow on. Okay, and about the laser, we're not going to talk about it in this class. If you're interested, we have a graduate level class on this. So, believe it or not, this simple thing here, 0, V1, V2, this quantum well structure, is actually too complicated to solve, at this beginning. Okay, so we will continue to simplify things. This is what physicists do. So what we will have in this class at the beginning would be something called infinite potential well, infinite square well. So what the infinite square well is to let V1 and V2 goes to infinity. Okay, goes to infinity. And why would that simplify this? When you let the potential well to go to infinity, what you're effectively doing is that what you mean is that your electron cannot go beyond this boundary, right? Because if you go into this area, if your electron go into this area, then you will have infinite potential energy, right? So unless you inject infinite energy to the electron, otherwise it will never come to here. Okay, so this infinite potential well, what it does is that it simplifies solving two things it does. First is that you no longer need to solve the Schrodinger equation in this region and that region, right? Because electron won't be there. Okay, x smaller than 0 and x larger than L, electron would not be there. So you don't need to solve it anymore. Okay, and second is that the mathematical expression of that is psi x will be 0 when x greater than L and x smaller than 0. Right? Because the amplitude square of your wave function represents the probability of finding an electron there. And if there's no probability of finding the electron outside the potential well, infinite potential well, that means your wave function has to go to 0. Okay, so this simplifies this thing into a simple boundary condition. Is that psi x equal to L equals to psi x equal to L equal to 0. Right? And then the thing would be you only need to solve the Schrodinger equation in the middle between 0 and L, and then you can use boundary condition, okay, of this. Okay. Any questions at this point? Now let's focus on how to solve this quantum well, this potential well. Okay, infinite potential well. According to the procedure we introduced earlier, the first step is to, of course, write down the Schrodinger equation, which is already here. And then you have to specifically write down the potential energy. So the potential energy is 0, x larger than 0, smaller than L, and infinity everywhere else. Okay, and then you also have to write down the boundary condition. Boundary condition we already know is psi x equal to 0 at x equal to 0 and L. Okay, and then initial condition, we right now we don't have it. Okay, initial condition can change. You can say, okay, I drop an electron in the center, that's one. Or you can say I measure the energy, and then the initial condition becomes the eigenstate, one of the energy eigenstate. So that one we'll talk about later. Okay, so now we focus on how to solve the eigenstate of this potential well. So the very first thing that you need to do, and then this actually you can do it for all the quantum mechanical problem, is to do the separation of variables of position and time, right? If you look at the left-hand side, this is your Hamiltonian. In most cases, your Hamiltonian is independent of time, right? Then on the right-hand side, you have an operator of time, and it's independent of position. So what you can do is that you can do separation of variables, saying that the eigenstate of the system can be separated into a function of position times a function of t. Okay, for eigenstate, not for any state, just for the eigenstate. And then if you do this, then you can plug this back in, and then we'll see what will happen, right? So you have your Hamiltonian operator act on your state of your function of position and then the function of time. And we know that this is a position operator. It does nothing to the function of time, right? So that the function of time, you can move it in the front because the operation has nothing to do with it. And then on the right-hand side, you can kind of see the same thing. Right, this is a differential of time, and it has nothing to do with your function of position. Right, so again, you can move your function of position in the front, okay, because it's just a number to the time operator. Okay, and now one thing you can do is to divide this equation. This is simply the Schrodinger equation, and then you do separation of variable. And then the next thing you can do is that you can divide this equation, entire equation, by psi n t and then psi n t x, right? Divided by the wave function itself. Right, and then what this would do is that you can cancel this. Okay, you can cancel this function and cancel this function. And then I think we talk about this, you can't cancel this too, because when you have operation of function, it will change the function itself. Okay, so they are not, you can no longer cancel each other. So what this will give you is that Hamiltonian x act on psi n x give you psi n x equal to I h bar t psi n t. Right, And then we also have explained this. If you look at the left-hand side, the left-hand side is operator of x, function of x divided by function of x. So the left-hand side is a function of x. It doesn't have the time components there. So you can say this is a function of x. And the right-hand side is also the same story. Operator of t, function of t, there's no position there. Okay, so on the right-hand side is a function of t. And then to let a function of x equal to a function of t at any possible time and any possible position, the only possible way to do this is that if they two equal to a number, right? Only if they are the number, then you can have them equal to each other at all possible position and time. So this equal to that, meaning that you have to equal to a number. Okay, and then the number that we label as E is because if you look at the dimensional unit of this thing here, you have wave function divided by wave function, and the dimension of these two will cancel each other, right? And then so the number left out here will have the same dimension as your Hamiltonian. And then we know that Hamiltonian is the operator of energy, right? So it should carry the dimension of energy, so that this number, okay, in the end eventually would be would have the dimension of energy. So then what we have would be your wave function, well, the Hamiltonian act on the eigenstate, okay, equal to En, your eigenstate. I shouldn't call it eigenstate yet, but when you look at this, okay, this is just an eigenstate equation, right? And then the other side you have any questions? Okay, if we look at the other side, the t components, you will see the differential of t equals to the function of t times En, right? Okay, and then this is a little bit straightforward to solve, because what it is that what it says is that if you move this coefficient to this side, what it says is that the differential of a function, first order differential function, gives you a number times the function itself, right? And then there's one common function we know that is the exponential. Right, it's the exponential. You just put this coefficient into the exponential. Right, when you do the differential of this, the coefficient come out, and then your exponential stay the way it is. Okay. And then this part is the eigenstate equation for Hamiltonian, okay, which is also called time-independent Schrodinger equation, which, to my opinion, is a very bad name because it's just an eigenstate equation. It doesn't, it doesn't capture the fact that you have a Schrodinger equation there. So, and if you take a look at this, what you see is that, okay, this separation of variable, we didn't even use the fact that we're doing a quantum well. Right? The only thing we use, the only thing that we assume is that the Hamiltonian operator doesn't have time in it. So this separation of variable applies to all quantum mechanical problems as long as your potential well is not time dependent. Right? If you have an electron in a time varying electrical field, then of course you can do separation of variable like this. There will be a time varying electrical field there. But if not, then you can actually apply this to any quantum mechanical problem as long as your Hamiltonian is time independent. So in the future, in the problem in this class, what you can do is that you can jump into here directly. Okay, you can skip this separation of variable step, and you can jump into. Let me write it down here. You can jump into saying that I have a Schrodinger equation, and then that will give me psi n xt eigenstate. The eigenstate would be an eigenfunction of x, and notice that the notation is in general the same. Okay, between these two, this is the way that people do, although it's a little bit confusing. And then times exponential minus I e n divided by h bar t. Okay, so this is your eigenstate of the Schrodinger equation. Okay, of the Schrodinger equation, and then the way to solve this is you can apply the time independent Schrodinger equation or eigenstate function of the Hamiltonian. Okay. Then your job becomes solving this. Solve a differential equation. And then from here, it's basically a math test. It's nothing about physics, okay? And then eventually you will see, okay, for any state, then apparently it's a superposition of all these possible eigenstate. Okay, and then we already said that to figure out the alpha n, you need to use the initial condition, and then we'll actually cover this a little bit later. Now we have 5 more minutes. We can actually, first of all, any questions to this point?
What's the difference between so you mentioned, like, you refer to two things as psi, one that looks like a P and then one that looks like a trident?
You mean these two? These two?
Like way at the bottom, I feel like would be a better example, where you have that equation and then right above it, you have another equation.
Oh, this one. It's the same thing. It's just different notation.
Oh, okay.
Yeah, so in the beginning, I use different symbol because I don't want to confuse you. But then in the real world, people do this confusing thing. Okay, they just drop the T, and then that's it. Yeah. So yeah, so it's better to keep our notation the same as all the textbook.
Right.
Okay. Yeah. Any other questions? Okay. If not, then we have 4 minutes. Well, 3 minutes. And let's solve this Schrodinger equation. This one is fairly simple. So the Schrodinger equation is that inside this potential well, you have potential energy is 0, right? So you have this. All right, this is your time-independent Schrodinger equation inside the potential well. And apparently, okay, you guys, probably some of you already see the solution here. What it is that the second order differential of a function is the function itself with the number, right? And then the simple solution for this is sine and cosine. Because if you if you do a differential on sine, it becomes cosine, and then if you do a differential again on cosine, it becomes minus sine. So you actually get return to the wave function itself, and then you get a minus sign, right? So naturally the solution for this is you can have sine kx. K is a value that would later be determined by this coefficient, or cosine kx, right? Both of these are possible values, possible solutions. And then next is that you need to apply the boundary condition now, right? Because otherwise the k can be any value. So boundary condition you can see is that, okay, the psi n x equal to 0 has to be 0. And that cues the cosine, right? Because cosine knx at position x is always 1, right? So that means your wave function is sine knx, okay? Now, second boundary condition we have written down here is psi x equal to L equals to 0, right? So what it is sine k and L equal to 0. Means k and L in principle equal to 0, pi, 2 pi, and keep going. It's m pi, right? Say m pi. And then apparently if k equals to 0, it doesn't make any sense, because then you just have a 0 function. It means you have 0 probability of finding electron in the potential well, meaning that your potential well doesn't have electron. So there's nothing to start with. Okay, it's a boring solution, trivial solution. So you can drop n equals 1. So what you get is that Kn equals to n pi divided by L, and then n equals to 1, 2, 3, and keep going. Okay, and that will take 1 more minute. And then if you plug in this to the time-independent Schrodinger equation, then what you will see is that whenever you do a derivative, you get the Kn out. So eventually what you get is En equals to h bar square Kn square 2m, okay, equals to h bar square pi square n square 2ml. Okay, and then psi n is sine, well, there's a normalization factor here. We haven't normalized it yet. Okay, so this is the solution of the this is the eigenstate of the potential well. Okay, infinite potential well, and then this is relatively simple, and then unfortunately this is the only simple one. Okay, we can find, and then from now on it will be more and more difficult. Okay, and then in the next class we will talk more into detail of how to do the normalization, and then how we can do measurement based on these solutions, and then connect this kind of solution to the experimental measurable results. Okay, so that's all for today. I'll stay here for a few more minutes to answer questions.